first set. So we're focusing today on ratios, proportions, units, and percentages for the SAT. And we're starting here on Thursday. 240 adults and children attended a show. The ratio of adults to children is 5 to 1. How many children do we think attended the show? How many children attended this show? 40. How'd you get 40? Uh-huh. Okay. Yeah. So that works. We're looking at a ratio of 5 to 1, right? Adults to children. Okay? Which, if you have 5 adults and 1 child, how many people is that total? Right? So if we're looking at children, 1 out of every 6 people is a child. So I have a ratio of 1 to 6, or 1/6. I take that and I multiply it by 240. That gives me how many children are at the show. What do you say, ratio? That's a ratio. That's a ratio, that's a ratio, that's a ratio. A ratio is comparing 2 things. So comparing the quantity, all right? So comparing the quantity of 2 different things. We're focused on children, how many attended the show. So 1 out of every 6 people at that show was a child. So if I do 1/6 times the total admission, I get the number of children. So that's where I get the 40. If I wanted the number of adults, what would my ratio be instead? This is children. What would my ratio be for adults if I wanted the number of adults? 5 to 6. 5 to 6 times the 240 would give me the 200 adults that went to the show. Okay, so we're comparing the 2 things, adults to children. All right? Questions on that? Okay. So, yeah. What do you say? All right. At a given location, time of day, it might be true that a fence post that is 4 feet high casts a shadow that is 6 feet long. What is the ratio of the height of the object to the length of the shadow? So I want the ratio of height to length. The ratio of height to length. So what's the height? The height is 4 and the length is 6. Okay? There's a couple different ways that you can write or that you will see ratios. Okay? The colon is really common. Okay? 4 to 6. We could also represent this using literally the word 2. 4 to 6. Okay? 4 to 6. All right? Most common, however, is the fraction. And then when we have the fraction, we simplify. What's 4/6 simplify to be? 2/3. Okay? So that means for any given object, for every 2 feet tall that it is, the shadow will be 3 feet long. Okay? For every 2 feet tall, the shadow will be 3 feet long. All right? Now, what we're going to do is we're going to take this ratio and we're going to use it on this. So I have a ratio of 2 to 3. Okay? Every 2 feet tall is going to be 3 feet long on the shadow. All right? 2 feet tall to 3 feet long. All right? So with the same ratio, how long of a shadow would a 6-foot tall man cast? How long of a shadow would a 6-foot tall man cast? How do you know?
It's 2 to 6.
So we end up getting 6/9. That's the same ratio of 2 to 3. 6/9. Foot shadow. 9-foot long shadow. 9-foot long shadow. Okay? Now, we're going to end up with this, with a relationship, and we'll see that in just a minute. Okay? So, how tall would an object be with a 12-foot shadow? So again, we've got the same ratio. Same ratio of 2 to 3. Okay? And I want to know how tall the object would be if I have a 12-foot shadow. How tall would the object be with a 12-foot shadow? 8. Okay. Again, gives me that same relationship. I'm comparing height to length. Height to length. I need to end up with a ratio that is always equivalent to 2/3. Okay? Now, talk about this real quick, okay? That 2/3 is what we call the constant of proportionality. Constant of proportionality is just the ratio comparing two things. Now, using that constant proportionality, we can write these equations that model scenario. We call these proportional relationships. If I graph these on a graph, all right, if I graph the relationship of the length to the height, let's say this is height and this is length, it's always going to start at the origin and it's going to be this constant ratio. Okay, it's going to be a straight line for every 2 feet tall, 3 feet long, 2 feet tall, 3 feet long, 2 feet tall, 3 feet long. It keeps going up and up and up. So at any point, I can find what those corresponding values are going to be. Okay? Now, the constant of proportionality, when we move on to other linear problems, ends up being the same thing as slope. Okay? It's that rate of change also is that comparison between the two values. And knowing that and understanding that process, we can write an equation that models the scenario. On the last two problems, okay, these numbers easily converted from one to another. I can see how to get from 2 to 6, so I apply the same process to 3 to 9, or 2 to 8 from 3 to 12. Okay? But understanding this ratio, understanding that the height is always 2/3 of the shadow, allows me to get the equation where height is 2/3 the length. It lets me use that proportion to write an equation. All right? So that's our basics of our ratios and our constant of proportionality. Now, another big thing with ratios is unit conversion. Okay? We use ratios with unit conversions a lot. And the big thing to pay really close attention with unit conversion is specifically, are they the same units? All right? You need to be very, very careful when you're talking about your unit conversion. So, Erica plans to purchase seed to plant grass in a large field. She has a map of the region and calculates the area of the region on paper to be 180 centimeters squared. Okay? The scale on the map is 1 centimeter equals to 20 feet. Okay? Now right there, I want you to notice something. What's the difference between the 800 centimeters squared and the scale that they gave me? What's the difference between the area of the map and the scale that they gave me? It's different, squared. So if I wanted to figure out the area of the region using this scale, I'm not going to get the right conversion because this converts centimeters to feet, not centimeters squared into feet. So I need to adjust this to get a new conversion. Okay? So right now I have a ratio of 1 to 20. Okay? That's centimeters to feet. Okay? But I need area. Okay? So area is just length times width. It's squared, right? So if I have 1 centimeter equals 20 feet, if I square both of those, it's going to turn it into area. Okay? Well, 1 centimeter squared is just 1 centimeter squared. Okay? 1 squared is 1 centimeter squared is centimeters. Now, what's 20 squared? 400. So now I have a new ratio of 1 to 400, and that's comparing centimeters squared and feet squared. So when you're dealing with versus area units, you need to be really careful and make sure you're using the proper ones when you're doing that conversion. This kind of stuff happens all the time. It's a really easy one to trip you up if you're not paying attention to the linear and the squared. It's a quick conversion. It's really easy to fix it, but you have to be aware of that change. Okay? So now we actually have this calculation. Okay? So before we finish, let's go ahead and find the area of the actual field. If the field is 180 centimeters squared, I want to convert it into feet. Raise your hand if you've taken chemistry before, whether you're doing it now or if you've done it in the past. Okay, most of you. Dimensional analysis, unit conversion. You do unit conversion a lot in chemistry. This is what we're doing. Okay, it's also called stoichiometry. All right, so 180 centimeters squared, I want to convert it into feet. Whatever the unit you want to end with is the unit that's on top in your ratio. So if I want to convert centimeters into feet squared, centimeters squared into feet squared, I'm going to multiply by the ratio of centimeters squared to feet squared, but I want feet squared to be on top because that's the unit I want to end with. Okay? 400 feet squared for every centimeter squared. Because what happens with my units here when I multiply? What happens with the centimeters squared? Okay? That's that dimensional analysis there. That's that unit conversion. If I have centimeters up top and centimeters on the bottom, centimeters cancel. Now I'm just left with feet squared. So when I do this multiplication, it's going to give me the area of the entire field. Okay? In real life. Not just on the map, because that's 180 centimeters squared. It's going to give me the actual square footage of the large field. Now let's continue reading. If Erica plans to cover every 400 feet squared with 1 pound of seed, approximately how many pounds of seed will she need? There's another ratio there. Okay? We have another ratio. What ratio did we just get there? $400 feet per pound of seed. Another ratio. 1 pound of seed to 400 square feet. 1 pound of seed for 400 square feet. That's another ratio. So I have the area of the field, and now I'm going to convert it to pounds of seed. How many pounds of seed? So again, I'm going to include my unit conversion. I want to convert the area into pounds. I want to end with 1 pound. I want to end with pounds. Covers 400 square feet. So what happens there? The 400 feet does what? Just cancels. The feet squared cancel and the 400 cancels. So this type of question isn't meant to test your calculation abilities. It's meant to test your unit conversions and understand what those conversions mean. Because based off of this unit conversion, how many pounds of seed do I need? What's left? 180. 180 pounds. From centimeters and feet to centimeters squared and feet squared. Centimeters squared to feet squared, and then area to weight. Or volume. Okay? So, that's it. We didn't really have to do, except for this right here, that's the only calculation we did. Everything else was canceled out. Did one math step. Everything else was just writing out the units. Go ahead and take a look at the next one, the next slide on the dimensions of the room. Go ahead and find the area of that room using the scale. Go ahead and find the area of that room. Architect's drawing on a floor plan for a house. 1 inch represents 3 feet. If a room is represented on the floor plan by a rectangle that has side lengths of 3.5 inches and 5 inches, what is the actual floor area of the room in square feet? to do might be to convert your side lengths from inches to feet. Then find your area. Convert your length and your width into feet first before you find the area. If you found the area in inches squared and then converted it to feet, you probably got this number because you're off by a factor of 9. So it's easier, make sure that before you convert to area to have it in the proper units first. Otherwise, you need a different scale. Just like we did on the last one with the area, I had to convert my scale of centimeters to feet into centimeters squared to feet squared. I could do the same thing here if I converted my scale. If I have a 1 inch to 3 foot scale, well, in order to get area, I'd have to square it. 1 inch squared equals 9 feet squared. So if you found the area first, which you can do, 3.5 times 5, get that, and then multiply it by 9 instead of 3. Very, very aware of what your units are, whether you're dealing with linear or whether you're dealing with area. Okay? Questions on that? Okay? Now, conversion within the metric system. Okay? So far today, everyone's looked at this and been like, wait, what? How do you convert? Way easier than converting within imperial, I promise you. Okay? Metric system. Huh?
Just not stick to one and not.
Because people suck, that's why. You gotta have both, because they'll use both. Yep.
And the SAT.
They'll have imperial and they'll have metric. You may have to convert between imperial and metric. They'll give you the conversion rate, but you'll need to be able to convert from one to the other. Okay? So, I have kilometers. Okay? This tectonic plate moved 1,060 kilometers in 10.3 million years. What was the average speed of the plate during that time period? In centimeters per year. So I need to convert kilometers to centimeters and millions of years into years in order to get my speed in centimeters per year. Okay? So again, we're looking at 10,060 kilometers. How do I convert kilometers into centimeters? How many centimeters in a kilometer? So, here's a trick. Those are the abbreviations of all of the prefixes in the metric system. Kilo, hectare, deca, your base unit, which is either liters, grams, or meters, deci, centi, and milli. Okay? There's an acronym. Are you ready for this? King Henry died by drinking chocolate milk. Apparently. And it hurt him real bad. Okay? King Henry died by drinking chocolate milk. And that gives you the prefixes for all of your metrics. So to go from kilometers to centimeters, or for hectoliters to milliliters. Okay? You can use that, and it's a base 10 unit. So every single time that you move, you're either adding or removing a 0. Okay? If you're going from a larger unit to a smaller unit, you're adding a 0. If you're going from a smaller unit to a larger one, you're getting rid of a 0. So it's just moving the decimal point left or right. So if I'm going from kilo to centi, I have to move 1, 2, 3, 4, 5 times to the right. That's adding 5 zeros to the end of my number. So 10,000 or 1,060, 1, 2, 3, 4, 5 zeros get added to my number. Okay? So that turns it into from kilometers to centimeters. Now, 10.3 million, now I just got to write out the number of zeros per million. So I have 10.3 million. So 10,300,000 years instead of millions of years. Now what's the easy way to divide when I have a bunch of zeros? So now I'm just left with 1060 over 103, which is approximately 10.3. It's like 10.29. Oh. So yeah, you'll be expected to go back and forth within the metric system. Okay? If they want you to convert across metric to imperial, they'll give you that. They'll say per miles to kilometers, use this conversion rate. And they'll tell you number of miles to kilometers. You have to remember those. But within the metric, it's a base 10 unit. You should be able to do the acronym help sheet. If I wanted to go from, let me say, 763 centimeters to decimeters. Okay, I wanted to go to decimeters. Centi, 1, 2, 3 units to the left. I take my decimal place, 1, 2, 3 units to the left, 2.763 decimeters. Decameters. Okay. Okay. So going back and forth in metric is just moving your decimal point left or right, however far it is that you need to go. Questions on that? All right. Okay, so now we're looking at 2 districts. One has an area of 30 square miles. 30 square miles. And a population density of 370 people per square mile. Okay, 370 people per square mile. Okay, so there's population density. And then we have another district that has 50 square miles with a density of 290 people per square mile. Okay, so 370 people per square mile and 290 people per square mile. And it wants to know the population density for the entire county. So what do I need to know? What 2 things do I need to find the population density of the entire county? I need the entire population and the entire area. So I need the total population and the total area. Okay, total population, total area. So let's find the population and the area of each district. Okay, if I have 30 square miles and a density of 370 people per square mile, how do I get the total population? Yeah. Again, just unit conversion again. I've got 370 people per mile squared. Multiply it by the 30 miles squared. So those units cancel. There's the population of my first district. I've done it 3 times. I've memorized most of these numbers. All right, same thing with the other district. 290 over miles squared times the 50 miles squared for that district. Did I get it right again, Kai? So then what's my total population? If I've got 11,100 and 14,500, what's my total population? 25,600. 25,600. That's my total population. And then what's my total area? I've got 30 square miles in one district and 50 square miles in the other. 80 total. And what does that give me? 360? 320. 320 people per square mile. 320 people per square mile. It's a whole lot of just ratios and conversions. Ratios and conversions. Ratios and conversions. Alright, last one for today, I think. Yep, last one for today. Furniture store buys its furniture from a wholesaler. For a particular table, the store usually charges the cost from the wholesaler plus 75%. Okay? So I want to write an equation to model that first. Okay? Cost from the wholesaler plus 75%. 75% of what? Of the cost. So I have cost again, right? So cost plus 75% of that cost. And that gives me the price that they sell it for on any given day. Okay? Let's simplify that a little bit. 75% as a decimal. 0.75. And then cost is going to vary, right? That's going to be variable. So cost, I'm just going to use X to represent cost, plus 0.75, again, X for cost, and that gives me the price on any particular day. Okay, on any particular piece of furniture. Now I can combine like terms. If I have X plus 0.75X, what does that equal? 1.75X. Oh, trust me, markups are usually 100% or more. Okay? So, they buy a piece of furniture from a wholesaler, multiply it by 1.75, and that's the price tag that goes out on the floor. Okay? So for any given day. Now, during a sale, instead, they charge the cost from wholesale plus 15%. So they change the 75% to the 15%. So how is that going to change this formula for the sale? So it'll be 1.15x, and that gives me the sale price. Okay, so the only thing that changed was the percent they add on to it. So instead of 75%, it's 15% of the cost. Okay? Now, the sale price of a table was $7.90. What is the usual price? Okay? So we need to find this. We were told this. Okay? We need to find the original price. We were told the sale price, and we have equations that model both. And X represents the wholesale cost, because that doesn't change. Luckily, wholesale cost doesn't change. So I can take this equation. I can start with 1.15X equals $2.99. Okay? So how do I find the wholesale cost of that table? By 1.15. Right? So the wholesale cost, $260. Okay? That's my wholesale cost. Wholesale cost. Alright, so that's how much the store paid for that table. Now, we want to figure out how much they originally charged for that table before the sale. So we take that, and we plug it back in with the 75% markup instead of the 15% markup. All right? So 1.75 to 60, and that gives us what, $455 was the original price of the table. Okay? Before the sale, $455. It's not bad. $150 off. Could be worse. So $450 is our final cost. Boom, there's B, $455. Okay, that was the original price of the table. Questions, comments, concerns? Now,